hopefully we are capturing the lecture. Oh, oh. All right. Let's see. Sharing. Share. Hopefully, I'm sharing the right screen. All right. Okay. So let's get started for today. So we're going to continue with dynamic programming, and we'll look at some more examples. Dynamic programming part 2. Okay, so so basically we're gonna look at some additional problems that can be solved with dynamic programming, right? And then so some of the canonical problems that we look at is going to be a version of the knapsack problem. Okay, and then another big one is basically what is known as DP on graphs. Like, how do you use dynamic programming to solve graph problems? And then we're going to look at shortest path. Okay. So what was the recipe for DP? Do you remember? Like, what are the steps? And it's the same recipe for all the problems.
You have to break it down into subproblems.
Before subproblems, what do you do? What type of problems do you solve with DP? Yeah, go ahead.
You need to find the recurrence.
The recurrence relation, right? The recursive formulation, where a bigger problem in terms of smaller problems. And then we kind of bound the number of subproblems, and then we solve the subproblems in a particular order, right? And we can also actually define the order, because for a DP to be correct, the subproblem should have dependency, which is a directed acyclic graph structure, and you kind of topologically sort that to get a linear order, and that's the order in which you can solve the problems, right? So that's kind of the recipe. So first is you find a recurrence relation bound number of subproblems, right? Build the DAG of subproblems, do topological sort, right? And solve in the top sort order, right? That's the recipe, and that holds for all problems that we look at. Okay, so now let's try to apply this to a new problem, which is knapsack. So what is the knapsack problem? So have you anyone heard of the knapsack problem? Okay, it's basically, you can think of, again, there is a fun way to think about it is, I heard a professor saying that if you're Indiana Jones and you're kind of fleeing from the temples, and where you need to kind of pack valuable stuff, and you just have a finite bag to carry stuff, then how do you want to fill it up if you want to increase your value, right? So your goal is try to kind of find the most valuable stuff and pick as much as possible, right? So similarly, if you have a backpack and you have a bunch of items to pick from, and then each item has a certain volume, right? So as your knapsack has a finite capacity, so you cannot pack everything. So the total number of items you can pack, the sum of the volume of all those items should be less than the capacity of the knapsack. But then each item has a value, and you want to maximize the total value of all the items that you can pick, right? So the problem, the input is you have a total capacity, let's call it W, and you have n items, right? And the items have a pair of values. One is a volume of the item, another is a value of the item, how valuable it is. So it's going to be W1 is kind of the amount of volume or space of that item, and then V1 is how much valuable it is, right? Okay, that's your input, and then the problem I'm trying to solve is you pick a subset. So let's call it actually small n. I'm going to pick a subset S of all the items, right, such that for all the items that you've picked in your set, so summation of the total weight of all the items must be bounded by your total capacity of the knapsack. Okay, so that's your constraint, capacity constraint, and you want to maximize summation of all the items you pick, the value of all the items, right? So that's your problem. Okay, and now again we apply the recipe. So is the problem statement clear, like what we're trying to do? Okay, now again, if you follow the recipe, first is what is the recurrence relation. Okay, so let's define the knapsack problem as Kp, okay, and then Kp has
sorry, I have a question.
Yeah.
Negative values or weights?
So we are going to assume that weights are positive in this case.
Values?
Values, I think you can have negative, but there is not much significance of considering negative values.
Oh,
Right?
yeah, just put
I mean, you can take all the values, add them, add a certain amount to make them all positive. Right? Value is like relative, right? What matters is of all the items, like it's like -10, one item is -7, the other one is -1, so -1 is more valuable. That's why that matters, right? So without loss of generality, we can assume they're all positive numbers. Okay, good question. So now let's think about a recurrence relation. So the problem I'm going to solve is the knapsack problem with n items and total capacity W. So I can write it like this. So n items and total capacity W, right? And then now again we actually apply a similar trick, right? Remember in the interval scheduling problem, what did we do? We considered two choices, right? We looked at the last interval after sorting them, right? And then we said we're going to consider the last interval, we're going to either pick it in the optimal solution or not pick it. So here we have n items, so we can do the same thing. So just consider the last item here, right, which is Wn Vm. So you can either pick it in your knapsack or you don't pick it, right? So like let's say I pick that item, pick item wn with value vn, then what happens? Then what is the remaining problem I have to solve?
Your optionality up to n minus.
You have to pick from the n minus 1 items, right? So in that case, the subproblem is AP of n minus 1. So, and then what happens to your total weight capacity?
It increases by Wn.
Increase or decrease? So all your items should have to add up to W. And now if I pick the last item,
You have picked up, okay, so then
so
it
I have picked it, so then the capacity is
decreases.
decreased. So it's what will be W minus the last item, right? And then if I don't pick it, then what does that mean? That means the optimal solution does not contain the nth item. So then my optimal solution, the optimal solution does not include the last item. So the
In our pick, I think you forgot to add on the n.
exactly, good catch, very good, excellent, very good. You're getting the DP stuff. So now if I don't pick it, then I still have to choose optimally from n minus 1 items. And then what is the total capacity?
Would be just W.
Just W, because I haven't picked anything. So I still have the full capacity at my disposal, right? And now that's your recalculation. Now there are two options. I'm trying to maximize my value. So what will I do of the two options? How can I combine the two options?
You do a max comparison, but also while checking your weight, making sure that's still possible.
Right. For that you just need like a base case. But whatever value you pick from here, you just take the max of it, right? So your mathematical relation is going to be knapsack with n items, and with W is going to be the max of Vn plus knapsack of n minus 1 with weight W minus Wn, right? And then for n minus 1 and W. Okay. So that's your recurrent solution. And then you will have some base conditions, and we kind of, when we look at the kind of the table or algorithm, we'll specify them. But this is basically your recurrent solution. And now the next task is kind of figure out how many subproblems we have, or bound the number of subproblems. So if you look at this relation, like what are the possible subproblems you have to solve? Like what are the values that are changing here from a smaller problem to a bigger problem?
It's just n changing by minus 1.
N changing minus 1, anything else?
Your weight is also changing.
The weight is also changing. So two parameters are changing. So what is the range of n? Just 1 to n, right? So number of subproblems is going to be the number of possible values of n, which is n. And now here is an assumption that we are making for this problem, is that the total weight is an integer, and all these weights, so W is an integer and Wi also is an integer. So this is an assumption for this problem, and we'll see if we don't have this assumption, actually the problem is NP-hard. Okay, we'll see why. But if you assume that all the weights are integers, then as you are varying the weights, how many different weights can you actually get?
You only get W weights.
W weights, right? So for example, if W, the value of W says 10, right? And then Wn, as Wn is changing, the smallest change is by 1. So it could be like W minus 1 equal to 9, 8, so on, up to 1 or 0, right? So that means that the number of subproblems is basically order of NW. Okay? So now you know that you have two the subproblems vary by either the number of items or the amount of weight, remaining weight. So you have kind of a 2D table here, right? And now all we have to do is kind of fill out that table and we are done. Okay? So so basically you're going to have a table like this where you have kind of N going from here and then you have W from here, right? So then basically your algorithm looks like this. You have this N problems and W, right? And then basically you're going to start with a table. Let's call it memo. And it's going to be basically a table indexed by the number of items and a weight value. And then now we're going to initialize this. How do we initialize? So for j equal to 0 to n, right? Memo j and 0, right? If 0 means that there is no weight available, so the solution with 0 weight and whatever number of items you want to pick is whatever amount you pick. Well, it's what memo j0, what this represents is that if you pick j items, if you try to pick j item and you have 0 items, 0 weight left, right, then how much value do you get? Nothing, because there is no weight left.
So you can't pick anything.
Can't pick anything, so it's 0. So this is kind of a base case here, right? And then the other base case is for right? This says that if I don't pick any item and I have weight k remaining, then the value again is you have left k weight left and you haven't picked anything. That's a possible subproblem, right? Because the subproblem is you can pick any n items. For whatever value you have remaining, if you don't pick anything, then how much value do you add to your solution? None, 0, exactly. Okay, so that's your base case. And now we fill up the table. Okay, double for loop. And now we have two cases, like we are looking at solving for item j with weight k, right? So you can either, when you are at the position jk, your recurrence is j in terms of j minus 1, right? So if you decide to reject the j item, then you're going to pick the solution that is stored in j minus 1 and weight left is k, the same weight left. But if you accept the jth item, then it's going to be the value of the jth item, which is vj plus memo j minus 1 and k minus wj, and then this is where your wait condition happens, right? So this only is true when this thing you add only if k is greater or equal to wj, right? If not, else you put the value to be minus infinity. Okay, so this is how you handle the case where you have negative weight. So if you after you subtract wj, if the weight becomes negative, that means that's impossible situation. So you just say that in that case the value is minus infinity, and then when you max, you're never going to pick that. You're going to pick the other option. Okay, and then finally at the end you just return. What do you return? Right. Oh, sorry. So I have to do memo jk is equal to max of the two values, rejected value and the accepted value, right? And then once the for loop ends, I just return the memo at the last position, which is m and w, and that's my solution for the full problem. Right? That's the value I return. Okay, make sense?
One question for the base case, the second base case.
Yeah.
Why are we doing memo 0, k is equal to 0? Wouldn't we want to, since it's just the index, that's what the 0, k equals 0 means, it's just the index, wouldn't we want to add on?
Well, you are adding on in the table when you're going down, right? So basically this is like what is happening, right? Like this is all 0. Right?
So, sorry for being nitpicky, but doesn't that mean that the array would be n plus 1 and w plus 1 size?
Why?
I'm trying to think through what the cases. This seems a little counterintuitive that both our base cases are 0. So every step we're adding on our value. If our width of our array is w, then we can only add on w minus 1 values. Does that make sense what I'm trying to say?
So here, so this should be 1. Is that your question? This is w1. Is that it? I mean, it doesn't matter. Like your array size can be, you can make array size like n plus 1 and w plus 1. Yeah. So your size of the array, you initialize it to be size n plus 1 times w plus 1, so that you have a 0, 0 position. That's perfectly fine. Okay, but now what is the runtime here? The time complexity? For every the amount of work for here, you just have a constant amount of work, right? For every value of j and k, and j and k can range from 1 to n and k and 1 to w, right? So nw subproblems, each one constant work, so the time should be order of nw, right? So that's polynomial time, right? And again, now here we have to think about the assumption, right? So let's say that w is not an integer, then let's w can be an arbitrary real number. Then what happens?
Well, we can't store it in an array.
You can store it in an array, and kind of the time also, because if w is not an integer, there is no way to kind of, basically if you can only approximate or partition w in finite intervals, which doesn't cover everything, right? So that means that basically the number of possible weights that you need to consider is infinite, right? So basically that becomes NP hard, right? So if w is a float or a real, the knapsack is NP hard. Okay, and then you need approximation algorithms, which again can use dynamic programming if you want. Okay, so because if w is not an integer, if it's a float, then basically the number of subproblems becomes infinite, and then there is no way you can solve it in polynomial time, right? It's going to be exponential time. Okay. All right. So let's move to the next problem. So next problem is called chain matrix multiplication. Okay. What is the problem? What's the input? We have a bunch of matrices. Right? So the input is a number of matrices. Let's say k of them. Okay. And then the dimension of the ith matrix is ni times ni plus 1. Okay. And the problem is going to compute the product of all the matrices. Right? And then if you have two matrices in general, let's say A is a matrix which has dimension m times p. What does that mean? The number of rows is m and the number of columns is p. And if you have another matrix B, so how many rows does B need to have? P. Right? So you need to match that times n, and then you get AB, which is going to be m times n. And now for this problem we are going to assume that multiplying just two matrices, we are going to use a naive algorithm, right? What is the complexity of the naive algorithm?
Multiply each element in A by each element in B, so it should be n by p, times p by n.
In matrix multiplication, if you recall, right, if it's like this, so this is 2 by 2 times 2 by 2, right? You kind of take the first row here and the first column here, and you do the dot product of them, right? So then you get one item here, one in here, one in here, one in here, right? So you have to do this for all possible combinations that you get in the final output, and then for each inner combination, this time, which is the common index here t. So the vector dot product takes time t, but you have to do this vector dot product for m by n times, right? So the complexity is m times e times n. Right? So this dot product, this computation is going to be order of m e n.
That's correct, but why isn't it 2p? So I can miss it.
2p, how do you get 2p?
Because you're doing p in your row, and then you're doing p in your column for every dot in the n by n matrix.
So so there are, in the dot product, there are how many multiplications? P multiplications. So it's
Oh, yeah, that makes sense. Okay, I'm sorry.
so there is some assumptions here is that when you have two numbers, when you multiply them, that's costly, but when you do the addition, that's kind of not that much costly. Or even if it's 2n, it's the order, right? So
Yeah.
you can ignore that.
Okay.
That's kind of the idea. Yeah. Okay. So now I want to. So now basically I have these matrices up to, let's say, AK, and then I need to multiply the matrices. So what's the problem here? Like, why am I even considering this for dynamic programming? Because I have a bunch of fixed matrices and I need to, is there a way to think about this problem where if I do something different, I can minimize the cost? So maybe let's give an example that would help us understand. Okay. Before that, we should recall some properties of matrices. Right? What is an important property of matrices? Let's say I have matrices A, B, and C. How would you compute it? Assuming now, in this case, that the dimensions are properly matched up.
You can either do AB times C or
Mhm.
BC times A.
Exactly.
But for does matter.
Right. So this is called associative, right? Right. And now let's look at an example. Let's say my matrix A is n by n. Right. So it's n by n. And then my matrix B is n by 1, so it's kind of just a tall column. And my matrix C is 1 by n, so it's just like a row. Right? And now, if I do, there are two ways to multiply these three matrices, right? So if I do the first way, if I first do AB, then to do ABB, the cost is n times n times n times 1, which is going to be n times n times n, right? And then, and this, the dimension of this is going to be n times 1. And now, if I do AB times C, this dimension is n times 1, and this is 1 times n. And then this again takes, the complexity of this is n squared, and the complexity is again is n times 1 times 1, so n squared, right? So again, this is n squared. So the total complexity is going to be n squared plus n squared, which is order of n squared. Okay? And now if I do it in the other order, if I first do BC, right, then what is the cost of doing BC?
Cost also to n by n.
N by n, so n squared, and then you get an n by n matrix. and then now you do A times BC, and now this is n by n and this is n by n. So what is the cost? This is n cube. So that's a bummer. So now the total cost for this is basically n squared plus n cube equal to order of n cube. So the order matters. So that's why we need to figure out basically which order in which we multiply the matrices. So that's why it's a dynamic programming problem, where we need to figure out the best way to order the matrix multiplications, right? So just to think about this problem, this is secretly a tree design problem. How is that? Which is very interesting, right? So how is it a tree design problem? So let's say I have 6 matrices A1 to A6. Right? If I have 6 matrices A1 to A6, right, then I need to multiply all these matrices, and then I can choose which ones I multiply in which order, right? So it's perfectly fine if I say that I'm going to first multiply A1 and A2, right? So I'm going to multiply A1 and A2, and then I get this matrix, right? And then I can say I'm going to multiply next. The next multiplication is going to be A3 and A4, right? So you can think that as I'm multiplying these matrices, I'm getting rid of these, and I'm just now using these as the next things to multiply, right? And then what can I do next? I have a lot of choices, right? I can choose to multiply A5 and A6, or I can take this one and multiply by A5, right? So if I do that, then I can get another node in the tree, right? And then I can choose that I'm going to take this product and this product and multiply them together. So then it's going to be A1, A2, A3, A4, A5, and then finally my full product is going to be this one, right? And if you think about it, this tree corresponds to a way of putting parentheses around these matrices, right? So for example, this one would be, I did A1 and A2 first, so A1 and A2 first, so I'm going to put parentheses saying that this is what I did first, and then I did A3 and A4, and then A3 and A4 got multiplied by A5, right? And then we did these two, then I did this one and this one, so that's another thing, and then finally I put A6 at the end, right? So that's the order in which I multiplied them, right? And now this should give you an idea of what is a possible recursive strategy to solve this problem, right?
Will the parentheses will there always be the same amount of parentheses no matter what tree you build? I'm trying to think of a scenario where you have extra nodes in the tree.
So let's think about it like we have, like, let's say I have n matrices that I need to multiply. How can I split this into subproblems?
You could either
So if you look back at the tree, like if you think about if this is like a, let's say this is a binary tree problem for you, right? Which is true in this case, a binary tree. How do you do recursion on a binary tree? You look at the root and think of the left subtree and the right subtree. So if this is the root of this tree, what does this split represent? This represents multiplying A1 to A5, the product of that with A6. And what is the order of that multiplication in terms of all the multiplication that we're doing in this problem? When do you perform this? Do you perform it at the first multiplication or somewhere else?
Oh, left goes first.
Right. So this one is the
very last.
The very last one. So again, you're splitting on the very last partition. You're deciding where would be the last split happen, right? So in this case, we decided that like this decision of the last split is that we decided that the last split is between 1 to 5 and 6. That's my choice, right? And if my else, I can also do like maybe 1 to 3 and 4 to 6, right? So I can basically, if I have A1, A2, A3, A4, A5 and A6, I can either split here, the last split, or I can do A1, A2, A6, that would be splitting near the end, at the beginning, or I can do A1, A2, A6. So I can split anywhere, that will be the last one. And wherever I split, now I have two subproblems.
Yeah.
So that's the recursive idea here, right? And now how many subproblems do we have? So now let's give this, look at the example. Let's say my split was A1 to A5, and I split here, right? So if I split here, my original problem was, let's call it matrix multiplication, MM for matrix multiplication of 1 to 6, right? That's my original problem. And if I split between A5 and A6, then this problem becomes a subproblem of what range? 1 to 5. And this becomes a subproblem of just 6, so we can say 6 to 6, just to make it formal, right? And then these are my two recursive subproblems. Okay? And then that means that in general, in my list of matrices, a subproblem is going to have basically a starting index and an ending index, right? And then what is the range of these indexes? From starting to end. So basically, if I have n matrices, it's going to be n by n possible subproblems, right? So again, we have n squared subproblems, right? And a subproblem looks like this, like mm from I to j, right? Where I can range from 1 to n, right? And then j has to range from, like, it should be from I plus 1 to n, right? Because j needs to be greater than I in this problem, okay? But that means both I and j, they both are kind of the total range is going to be, they both span n square possible subproblems, okay? Now with this we can actually now write up the code.
We still have another prediction in that one.
Which one?
I don't understand why it's n squared.
Oh, what is the possible value of I? I can go from 1 to n, so n possibilities,
Okay.
and whatever I you choose, j has to be from I plus 1. So like let's say I have 1 to dot dot n, that's I, right? And then j, if you think of a matrix, right, j has to be basically greater or equal to I for a subproblem. So in terms of matrix, it's going to be the upper triangular matrix. Okay, that's the technical number of subproblems, which is still quadratic, right? Does that make sense? So I just crudely said it's n square, but it's actually like half of the half of total of n square.
Yeah, we're getting that half problem. It's confused. If you pick a range from 3 to 5, that means that you have 3 subproblems, right? And you have 1 to I to j, j to n. Am I thinking about that the right way?
So what, like let's say A1, A2, A3, A4. My first index is just pick an index, 2, right? So that means that you're going to start here
Okay.
and then you're going to end somewhere.
Okay.
And the ending index can be 3, 4. Yeah, so that's, this is I and this is j.
Okay.
So j is always greater or equal to I.
Okay.
That's what I'm saying.
I agree with that. How are you getting n squared cases from that?
I'm getting order of n square cases.
I'm not seeing why it is.
I mean, if I do a for loop for I equal to 1 to n, j equal to I plus 1 to n, how many iterations do you have?
Yeah, n squared iterations.
N square iterations,
What
order of n
happens to
square.
your a of 1?
What?
What happens to your a of 1? So your I is 2, a of 1 is left out of this calculation, right?
So this part is not there.
Yeah. Okay, maybe
It's
that's
still
just
O of n square.
Okay.
It's half of your total 2D array. So think about it. This is a classic problem where you have ordering of the indexes, right? It's still n square. Okay. So let's quickly write the code for this. So you have a base case where right? What does this represent?
It's a base case.
It's a base case where you basically have,
Two x's multiplying with each other.
right, so when I do this, I'm going to initialize this as 0, and what I mean by that is this right end is one more than my range. So basically in this case you just have one matrix, so you don't have any multiplication to do. Okay, that's just for a convenience. Okay, and then in this case now you have the case from even I'm going to do I plus 2 because from I to j I'm going to ignore the right hand. So when I say my range is ij, that means I multiply matrices ai plus 1 dot dot ai I j minus 1. Okay, that's just a notational convenience. You can do it differently. Okay, and you can see that's why j goes to k plus 1, because when j is k plus 1, actually I'm multiplying up to k, right? So it's still valid. Okay, and then let's consider, now I'm going to multiply matrices. Initially let's say it's infinity, and now I have the left end point of my range and j is the right end point of my range plus 1, and then I need to multiply. Now I have a sub problem of multiplying matrices in that range, and that's my sub problem. And then now I'm going to do a for h equal to I plus 1 to j minus 1. My cost is going to be, I'm trying to minimize the cost, so it's going to take the existing cost, and then I'm going to say it's going to be memo of so basically h is all possible places where I'm going to break the matrix into two parts, right? So it's going to be I to h, that's my left part, plus memo of h to j, right? And then plus, once I solved I to h, now I have one matrix and h2 is another matrix. So then those have to be multiplied. So I need to add that cost here, right? So that cost is going to be, basically it starts with I, right? So the cost of that matrix would have ni times nh times nj, right? That's going to be your final cost. And then finally, once you've looked at all the partitions, you find the minimum one, and that's what you set for the memo ij. Okay, so ij is going to be the mean cost. Okay, and then finally you return from 1 to n. Okay, that's going to be your final value that you return here. I think I did k. This should be k. Okay. All right. So just maybe when you look at it, just think about these dimensions, just with some examples, and it will make sense. Okay. But that's kind of the rough idea of this.
There's no better mathematical way of doing this than just
What better-
analyzing the cost and like trying to find the correct split to find the right cost.
What do you mean mathematical way? Like,
Well, it seems like such a simple like problem. Like you just gotta align the dimensions correctly, multiply in such a way that your dimensions line up correctly. I feel like there has to be a better way of looking at it, just like grouping the many matrices. Logically, I don't know how else to say it. But
you want instead of algorithm, you want an analytical formula for figuring out the best
Yeah.
combination. So that's possible, but this is a computational way of doing it. So there's obviously probably, you can probably prove that, okay, maybe like you can exactly find the split that would give you the best one. That's like optimization. Like if you do optimization, sometimes you have a closed form solution, sometimes you have to iterate through it. So this is like an iterative way. And then there is, if you have any software that needs to do this, like a matrix multiplier software, you're definitely going to use something like this. Because a lot of times kind of solving analytically is expensive. So in that case, especially dealing with large matrices, the closed form solutions are really expensive, so you might just use some iterative algorithm like this. Okay, so maybe take like a 5-minute break and then we'll restart. Okay. So now I said that we're going to look at dynamic programming, but then we're going to look at dynamic programming on graphs. That's really very interesting. How do you do DP on graphs? And then the problem that we kind of care about is shortest paths. Okay. So now we're going to look at shortest path in graphs. Right. In general, when you apply dynamic programming to graphs, it's usually always a path problem. Why is that? Because if you think about a graph where you have like n vertices, right? In general, there is an exponential number of paths in a graph between any two nodes, right? So that means that you need to have a clever way of searching through those paths to kind of find the best path. Right, which is where dynamic programming helps us. So, in general, in our problem, the input is going to be a graph, right? And then we can assume it's a directed graph. And then, if you want, we can also consider undirected graphs, but it's the same problem. And then we also have kind of a cost of the edges, so it's a weighted graph. So every edge has a cost, right? And then we have a definition which is, let's say I have a path, let's call it pi, right? Then the length of pi is basically the sum of edge costs on the path. Okay? So just to give a simple example, like something like this. This is ST. Then if I consider this path, right, then what is the cost? Let's call this path pi. Then L of pi, basically I just look at the edges on the path and just add them up. Okay? Plus 1 equal to 10. Thank you. Alright. So our goal is to kind of, for like, there are many variations of this problem. You've already seen Dijkstra, right, which is single source shortest path problem. So your source is given, you need to find the distance from the source to other vertices. And then you can also do what is known as an all pairs shortest path, right? So single source shortest path, we call it SSSP. Another one is all pair shortest path, APSP, right? What is all pair shortest path? For every pair of vertices, you find the shortest path between them, right? And then SSSP is just the sources given. So this has like n paths. You return n paths here, right? Because the source is given, but here you have to return n squared paths. Okay? And then for each of them, we need to find the shortest path, shortest or minimum distance, minimum cost path. Okay? So now let's talk about an important aspect. So when we did Dijkstra, what was an assumption that we made in Dijkstra?
That there was no negative weight.
No negative weight, right? So everything is positive, which is why in Dijkstra you can use a greedy algorithm. But if you have negative weights, we actually saw an example in a quiz that if you have negative weights and you apply Dijkstra, you may not get optimal path, right? So in general, Dijkstra will not work if you have negative edges, right? And now the algorithm that we are going to talk about today, they in general can also work with negative edge weights, but the case where they don't work is when we have what is called a negative cycle. Okay, and I'll define that. So in general, there are two reasons why you may not have a shortest path. Okay, so two causes for no shortest path. Okay, one is a negative cycle, and I'll give an example of that. And there is another one. Can you guess what is the other one?
Well,
Let's say shortest path between two given vertices S and T. Right? I tell you that it's between S and T. Right, it's disconnected, right? So you can have S in this one component and T in the other component, and there is no path, right? So that's exactly right. No path from S to T. Very good. Right?
Plenty of negative cycles in the real world.
Yeah.
Is on a truck driving between a bunch of houses.
Right. We should talk about what the negative cycle means, right? So what is a negative cycle?
probably a cycle that has a total weight that's negative.
Exactly. So if I have like S goes to some vertex like this, and then I say it's 1, 2, 3, 4, minus 3, minus 2, right? And if this is like the direction, then the total weight on the cycle is 4 minus 6 equal to minus 2, right? And now what happens if you have if you're trying to find the ST path from here, right? So if you just take this path and avoid that cycle, then you get 1 plus 2 plus 3 plus 4 plus 11. What is that? 15 plus 3, 18, 20, 21. And then instead of doing that, if you kind of come here, and instead of going here, you just go here, then you kind of decrease the total length by minus 2. Right? Is it 4 minus 10 minus 1? Exactly. So every time you go across this path, you will decrease the minus 1. So you can just go across this infinite number of times, and then your shortest path length becomes minus infinity. So there is no stable shortest path, right? So that's why the negative cycle is problematic, right? And so now there are two types of algorithms. Some algorithms say that, okay, if you have a negative cycle, I cannot do anything. So give me only graphs without negative cycles, right? And then there are algorithms that work even with negative cycles, but what they will do is that they can detect a negative cycle, and if there are no negative cycles, they will return an answer of the shortest path. Otherwise, they would say that, okay, my bad, there is no shortest path because of a negative cycle, right? So we'll look at both types of algorithms. Okay, so the first algorithm that we're going to look at is Bellman-Ford. Okay, and Bellman is the guy who invented the term dynamic programming. Okay, and Ford is another scientist whose name will come up in next flow again, Ford recursive algorithm. So he's another scientist who developed these algorithms. So first we're going to look at the single source shortest path version of this, where you can have negative weights or cost. Okay, so this should be 5 minus 1. Okay, and then we are going to assume in this case first no negative weight cycle. Okay, that will be our first assumption. And then the Bellman-Ford, the runtime, we're gonna find out, or the expectation is we're gonna get an algorithm that runs in time order of mn, where m is the number of edges and n is the number of vertices. Okay, that's what we want to come to. That's kind of what we're gonna get. Okay, and then again, as this class is about DP, it's gonna be another DP problem that we are solving here. Okay, and now again, if you want to do DP, what is the recipe? First we need to find a the recursive strategy or recursive subproblems, right? Right? So let's say we have, it's a single source shortest path problem. So let's say I have this kind of an idea. I'm going to define a quantity which is called d of s to t, and I'm going to say another parameter I. Okay, and I'm going to tell you what this means. This is the shortest path distance from S to T that uses less than or equal to I edges, right? And this is also called a hop bounded distance, where I have a bound on how many hops I can have in the path. Okay, and in general, when I say dsti, this is always going to be greater or equal to the actual shortest path between s and t. Okay, so ds comma t will represent the final answer that I'm trying to get at for all nodes of t. That's the shortest path. But we are kind of using an intermediate value, and this will help us define a recursive strategy. Okay, to give an example of this notion, so let's consider a simple graph here. So let's say I have a node S, I have another intermediate node, and I have T here, and let's say this is cost 1, and then I have this which is cost like 10,000, right? And now what is DST? What is the shortest path here? Length 2, right? And what is the number of hops here? It's 2 hop, right? So DST is the same as DST2, because DST2 means that the shortest path distance from S to T which uses less than or equal to 2 hops, and that is correct for this path, right? And now, what about if I want to compute DST1? So is there a path from S to T with at most one hop? There is, right? That's the other path. But the cost of that is 10,000, right? So this is cost 10,000, and which is greater or equal to the actual shortest path. Okay? So the idea is that if you kind of constrain the number of edges you can have in a path, right, you might miss opportunities for finding better paths. So if you kind of relax the constraint, it's easier for you to find a better path. That's kind of the idea. Okay, and now let's think of a lemma. The lemma is that in a graph with n nodes, if I think of this DSP comma n minus 1 is equal to DSP. Okay? What is DSP? DSP is my optimal answer, right? And DSP n minus 1, what does this represent?
N minus 1 hops.
At most n minus 1 hops, right? And now I'm saying that this is optimal, right? What is the proof? So we said that as we relax this constraint, so for example, let's say this value was infinity. That means I have no hop constraint. That means I can try to find better and better paths with that. So as I lower this value, it gets harder for me to find the shortest path. But we are saying that you only need to increase the hop count to n minus 1, and that will give you optimal. So you don't need to have like n squared edges. You won't be able to get a better path. So that's the idea. So why is that? Again, we are assuming here there is no negative weight cycles, right? So how do you kind of see that?
There's n minus 1 edges
Mm-hmm.
that you're traversing. That means that if you have more than n minus 1, that means that you revisit the node.
Exactly.
Therefore, you have a cycle.
Right.
Since it's not a negative cycle, you're going to increase your distance past
Right.
total value.
That's exactly right.
Necessarily.
So if you have if you have more than n minus 1 hops, right? Like if you have n hops means that you have to touch at least n plus 1 vertices, right? So you're gonna hit n plus 1 vertices, right? This is known as the pigeonhole principle, right? And if that happens, then that means that the path with n plus 1 vertices repeats one vertex at least, so it has a cycle, right? So it has a cycle, and we know that there are no negative weight cycles, so this cycle weight is positive, right? So it's kind of like this, where you have a cycle, right? And then this has a positive total weight, right? And then basically you can remove this cycle. And then you can decrease the length, right? So that means that you don't need n hops. You can do less than n hops, right? N minus 1 is the maximum hop length. If you have n minus 1 hops, that means you're going to traverse at most n vertices, so that there won't be cycles. Right? Okay, so that's kind of the idea. I didn't go through the full proof, but that's kind of the rough idea. And now, what we need is that we want to compute d of s of t, and for that we just need to compute d of n minus 1, right? And now we need to compute this recursively, okay? So now we need to think about what is the So what is varying here is we need to compute like BSV of I, where I can be any hop count, and I can have any vertex, destination vertex. I want to compute this in terms of V of S, any destination vertex, and I minus 1. Okay, so that's what I want to do recursively. Right, so I want to compute a path with at most I hops in terms of path from S to any other vertex in terms of I minus 1 hops.
Wouldn't you only care about the neighbors to V because that's your final destination?
Right. That's right. That's actually the kind of the idea here. Right. So you're hitting the right idea. Right. So if you have in some sense, if you have a possible path from S to V, right, and then if you want to find kind of the best path from S to V, it's like finding an optimal path from S to any neighbor of V, and then from here you just look at what is you kind of do the recursively find the cost from S to one of these neighbors, and then find which combination of that smaller optimal path plus the last edge cost is the better one, and that's your strategy here, right? So to be formal, this is kind of the idea. So from S, right, you can think of one neighbor, any neighbor of V, right? And then there is also paths from S to V, right? So we are trying to find paths with at most I hops in terms of paths with at most I minus 1 hops, right? Now there are two cases. One case is that the path from S to V already is using, because this is less than or equal to I hops. So I minus 1 itself is less than or equal to I. So if your path from S to V already is using less than or equal to I minus 1 hops, then that's one possibility, right? So that's this path here. This is already less than or equal to I minus 1 hops. Then you don't look at the neighbors. But then the other option is that this path, right? Now you want this whole thing to have at most I hops, and then this is 1 hop, and then this has to be I minus 1 hops, right? So that case is that this is I minus 1 hops, and this is just 1 hop, right? And now basically now there are two possibilities, and you find the minimum of them, right? So this is how I can write it. So the path from is going to be minimum over, and now this U can be any neighbor of V, right? So it's going to be all possible U such that there is an edge from U to V in the graph. Okay, we're going to search through all possible such edges, and then if we have this case, then that means that the total, if the path from S to V already has less than or equal to I minus 1 hops, then that's one case, and the other case is that it has actually exactly I hops, right? If it, in that case, you have to have this case where this one is I minus 1 hops. So that you can write that as d of s to u. You are now you are allowed only I minus 1 hops, and plus the cost of the edge from u to v, right? And this is when if d of s v of I, it actually uses I edges, right? Because if it uses actually less than I minus 1 edges, so otherwise if dsv of I uses less than or equal to I minus 1 edges itself, then actually we have what? D of s v I minus 1, because it's already using less than or equal to I minus 1 edges, right? So these are the possible recursive cases, right? So now as we are doing this, what are the variables that are changing as we look at different subproblems? The hop count is changing. The maximum hop count can be n minus 1. So it can be n minus 1 to 0. And then the other thing that's changing is the neighbor here, which can again also be n different vertices. Right? You can think it's like a degree, but we are actually using synchronous shortest path to all vertices d. So in general, you can think of this u here, right? This u can be any vertex. So in general, I can range from order of n, u order of n, so total subproblems is order of n squared. Okay? Okay? So that was our second thing, which is number of subproblems is order of n squared, right? Because s is always fixed, v can be any n nodes, and the hop count can range from 0 to n minus 1. And now we have this recurrence relation, right? And we now know all the subproblems. We just solve the subproblems in the particular order from small to large, and then we actually have the algorithm, right? And that leads to the Bellman-Ford algorithm. Which has a graph and a source, and then we do an initialization. So now we have a table, right? The table has two indexes. One is the hop count, we'll call it I, and another value is like the destination vertex t, because s is fixed here, so that doesn't count. And then we initially say this is going to be infinity, because we haven't computed any path, just like Dijkstra initially. And then the only case where this is 0 is when so I think we should I'm going to do this like this. So this should be ti. So from the source, if you don't allow any hops, then the distance can be, what is the distance? So what does this represent? This represents from source to source with 0 hop, what distance do I get from source to source? 0, exactly. That's just how you initialize Dijkstra, right? And now we do a double for loop. So I is the hop count. So I can go from 1 to n minus 1. That's the maximum hop count. And then for all vertex v in the graph, what do? Now we just apply the recurrence relation, right? So basically it's going to be b of, for that vertex v with hop count I, is going to be minimum over all neighbor u to v, right? We're going to look at, it's going to be the minimum of either the path from S to V already has less than or equal to I minus 1 edges, so in that case dvi is dvi minus 1, or it's going to be b of u I minus 1 plus the cost from u to v, right? So this does not depend on this edge, so it's also going to be the same. So it's okay if we keep it inside this minimum. Okay, and that's the algorithm. That's the algorithm 4. And finally, what do you return? You return just d n minus 1, because you have to return the distance for all vertices. That's why this Python style notation of, and then n minus 1, we showed that this, once we do up to n minus 1 hop, we have the optimal path. That was because of the non-ending cycle assumption. Okay, and now the runtime. What is the runtime? Again, we just count the number of loops.
Be vertex by vertex.
Right. So this part is O of n, and this runs for every vertex v, but then how much time does it take for this one?
That will take in total the amount of edges in the graph.
Right, so this is exactly, because this is proportional to time degree of the vertex v, and then we're doing the sum of degree of v, which is 2 times the number of edges. So that's why this part, this loop runs in order of m time, and that means the total runtime is order of mn. Okay, right? So in general, if a graph is sparse, then m is like just n, but if it's dense, then m can be O of n square, right? So for dense graph, this turns out to be O of n cube, right? And now, how would you characterize this this complexity? Is it linear? Is it quadratic? Cubic? Why is it cubic? Again, this is a trick question to kind of solidify an understanding of complexity theory.
Could you explain what the dense is?
The dense means that m is O of n square. Right? For example, the complete graph is dense because it has all possible edges. Okay? But then if m equal to A of n square, then this runtime is going to be order of n cube. But when we say a runtime, we say in terms of the input size. What is the input size of the graph?
It's dependent on how complete it is.
It's dense, so it has n square edges. But if you have a graph represent, we have to represent the graph as in the computer either as a matrix or an adjacency list. If it's an adjacency list, then how much time, how much space does it need?
It's an array to linked lists supports.
So it's going to be number of edges, right?
Okay.
Because every linked list has size degree of that vertex, and you have to do that for every vertex. So sum of degree is 2 times d. So if you do an adjacency list, it's still time proportional to the number of edges, which is n squared for dense graph. So your input size is actually, input is n squared, not n, for a graph, because that's the amount of space you need. So if you say n square, you call it like, let's say capital N, right? Then small n is root of n, and then this turns out to be O of n to the power 3 by 2. So it's subquadratic. So you need to be very precise about the complexity, right? The complexity is always in terms of your problem input size, right? Complexity.
Runtime complexity.
Right. That's your input parameter. Your input is the amount of space for your problem, and output is the amount of time it takes to run the program, right? So you always need to be careful about that. Okay. And then, so this algorithm assumes that there are no negative weight cycle, but there is a way to actually detect the cycle, which is if there is a negative cycle, then you can see that if you go up to hop twice n, right? If you allow up to hop twice and there is negative weight cycle, then actually you'll actually eventually end up finding there is going to be at least one vertex v, such that if you go up to 2n hop, you're going to end up in a cycle. And if you end up in a cycle, that means that once you go around the cycle, you're going to decrease the weight. So this value is going to be less than v of s v of n minus 1, right? So now if you want your algorithm, if you want this algorithm to actually detect negative weight, all you have to do is, like, instead of n minus 1, you go up to twice n, right? And then after you do that, if you see that for any vertex v, the distance of twice v is less than the distance with n minus 1 hops, then you give it a cycle. If not, then you say it is a twice hops. Yes, that's how you include negative cycles. Okay, so I won't give too much detail, but I'll probably send some notes on that. But so now let's kind of try to finish. So Bellman-Ford for all pair shortest path, right? Let's try to quickly kind of do that. If not, we'll take some time next class, which I don't want to do. I want to really start next flow. But there is obviously a brute force way for this, right? What is a brute force for all pair shortest path?
Get all paths, all possible paths.
No, like we already have we have an order of mn algorithm for Bellman-Ford single source shortest path.
Oh,
If I use this, how can I use this for all pair shortest path? What do I do?
you generate SSSP for every single potential source.
Right, so S now varies from, after S, instead of fixing S, we just instantiate Bellman-Ford single source path for every possible source vertex. And that means that the naive algorithm is going to be order of m n squared, because you have to do that for every n vertices, right? But then we should definitely try to do better, right? Because there are a lot of overlapping paths, right? So the key idea here is that so originally we had a recursion where we were doing in terms of d of s with any destination vertex and I minus 1. Okay, and now from here, if you want to do all pair shortest path, what we're going to do is that we're going to say that I want to find for any source to any vertex and I in terms of d from any vertex to any other vertex using half the path length. Okay, now can I do that? Why can I possibly do that? So I have a vertex, I have a path from S to V, which has like less than or equal to I hops. So this total path length is less than or equal to I hops. Now if I have an optimal such an optimal path, right, what can I actually do? I know the total path length, so I can obviously break it in the middle into two paths of equal size. And then if I break it in the middle here, right, so let's call this X, then this path, it will be size less than or equal to I by 2, and this path should be size less than or equal to I by 2, and then the total path is path less than or equal to I, right? And now this path is represented by D from S to X and hop count less than or equal to I by 2, and then this path is D of XV with hop count I by 2, right? Does that make sense? Now the one question is, why couldn't, so in the single source shortest path, we were decreasing the hop count by 1. And here in the all pair shortest path, we are decreasing the hop count by I by 2. Now one question I have for you is, can I reduce hop count by I by 2 for single source shortest path or not?
No, because
Right, why?
because you don't know that you're not missing a negative longer hop negative path.
Right. It's actually much simpler because you see that if it was, so here we are saying S to B, but S is not fixed here anymore because it's all pair shortest path. But if it was single source shortest path, S will be fixed. If S is fixed, this subprogram has S fixed, but look at this subprogram, this no longer has the source.
Oh, okay.
So that's why you cannot do this. You can only do it for all pair shortest path. Okay. So that's the reason. Okay. And now the new recursion is actually much simpler. What it is, it's going to be from any S to T. Let's say I want to find a 2i hop bounded path from S to T. That is going to be, I'm just going to take, X can be any possible vertex in the graph, right? So for all possible X, so I'm going to do min of X in V, and then I just take the path from S to X with hop count I plus D of X to V with hop count I. And now this is my new recurrence relation for all pair shortest path. Okay, and now how many subproblems do I have here? I just count the number of values here, right? S and T each can be n, and I can also be twice I. What are the value of twice I? How many values do I have here? So I definitely have n square subproblems, but what am I doing with I? If I start with, so we know that the hop count can maximum n minus 1, right? And then if this is n minus 1, in the recursive call, I'm halving it, making it half. So from n I get to n minus 2, from n minus 2 I get to n by 4, to n by 8. So what are the all possible values of I? And it's no longer n, it's less than n, right?
Yeah.
So if I take n and I half it, then how many times do I have to half to get to 1? Log n. So I varies from log n.
Okay.
So now the total number of subproblems is n squared log n. right? And then now basically we have the all pair SP Bellman-Ford. Now I don't have a vertex to start with, right? So I init STI, right? And now what is, I now have a, this is going to be infinity for all, and now I have a base case. What is my base case? So D of, now I don't have S fixed, so S varies, so D of S to T, and let's say I'm looking at most one hop, right? So this value can be, when can this be 0? Right, no edge, or actually this is when S and T are the same values.
There's one hop.
At most one hop. So S to S is also correct. So I'm just gonna say that, but, and then otherwise it's just one hop is equal to just the cost from S to T if this is an edge in the graph, right? So that's the initial base case. And now we have the original case. So I now varies from 1 to log of n, right? And then for all UV pairs in the graph, right? What do I do? I just have the recurrence relation, which is D of S comma T, and then it's going to be, what will be the hop count? So we are doubling every time, right? Up to log n times. So we start with hop count 1,
Right.
and next time it's going to be 2, and then 2 square. So the top down was from n minus 1, we got to, from n we got to n by 2, n by 4. But in the table we are starting with the smallest hop count, which is 1. So it gets, now goes twice, 2 square. So it is 2 to the power I. Right? And then finally when I becomes log n, we get to like n or n minus 1. Right? So that's kind of the idea here. And then this will be just equal to minimum of x in V, and then V of S to X to the power I minus 1, right? 2 less, half less, plus D from X to T to the power I minus 1. And then finally, when I'm done here, I'm going to return the all pair shortest path, which are n square numbers. So just return this array where the first entry is empty, and just this is going to be n minus 1. That's going to be all possible pair of paths from a source vertex to a destination vertex, right? And now, what is the complexity? The time complexity. It's easy to count from the for loops. So definitely there's going to be a log n here. The u and v gives me n square iterations for this. So this is basically a double for loop embedded here, right? So n square log n, but here we also have another n. So it's going to be n cubed log n, right? Is that clear?
The other n is because x.
X can be any vertex. The split point can be any vertex. Okay. So the complexity is O of n cubed log n. Okay. So basically, this is called a path doubling technique, because you're doubling the path, the hop count every time. So that's Bellman-Ford with for all pair shortest path. And now there is another algorithm which we are not going to cover, which is called Floyd washout. Follow the shortest path, and you can do that in O of n cube. So I won't cover that, but take a look at that. It's a similar idea, but there is some other recurrent solution that you can use here. Okay. All right. So that's the end for today, and so next class we'll start max flow algorithms. All right. Okay. Thank you.